Okay, we're going to get started here. So we left off with this setting up your own project, and I just wanted to go through a few more things, and then we're going to give you some time to work on something of your own choice. And just wanted to review how the workflow operates in Chisel. So we take a design, we send it through the Scala compiler, it produces bytecodes that are run, produces a graph, and then you either go produce C++ or Verilog. In the C++ direction, you use the G++ compiler or any or C++ compiler to produce the application, and then you run it in simulation. And we showed how you could actually then have connections back to Chisel to do testing, construct a test bench. Then Verilog, you can go and you can either, once you have the Verilog, with the Verilog backend, you can either get netlist, power numbers, area, all that with the standard tools, or you can do verification with VCS and waveforms. So one thing that is pretty useful as a technique of last resort is to do printfs of your state. So we have this support here where you can write printfs in your code, and they can be conditionally updated or conditionally executed, and you can build up strings as well. And this works for both Verilog and C++ backend. We have a limited set of format specifiers. And then we also have assertions, which allow you to test that certain conditions hold while you're running under simulation. So both of these only run under simulation. So this would run 410 cycles and then terminate your simulation. Okay, so if you do want to install on your laptop, we have instructions online, but here's the basic idea is that you have to get your basic tools set up. We've had on the Mac it's Xcode console tools, and then on Windows it's using Cygwin, and then everywhere you got to install Git and Java runtime, and I guess this is supposed to be 4.8. Okay. And then here, moving beyond the boot camp, there's a bunch of documentation that is available on the website. There's a new document called Getting Started, which takes what I've done here and writes it up in written form. So it's meant to be a way that you can step-by-step kind of learn the basics with running examples. And then here, the Chisel project is on GitHub, so you can look at all the source code. There's instructions in the README that tell you how to install, like your Hello project, same kind of thing. The standard library, you can look at that one file under the Chisel directory, source main Scala. Chisel utils, it shows you a bunch of the standard libraries, and those are also described in the manual. And then there's a bunch of stuff in the download page. SODOR is this set of educational microprocessors that Chris Celio did, who's in the room, that implements the RISC-V ISA. And it's also a good source of examples for Chisel. And then we also have an easy installation where if you run VirtualBox, you can get all of Chisel and RISC-V infrastructure as one install file. So it's all configured for you. You can just run it using VirtualBox. That's a pretty easy way to get started. And I could only go over the basics of Scala. There's a couple of good books if you want to learn more about it, and there's a lot of online stuff as well. Okay, so we're moving into the project period, and we've set up a bunch of examples that you can take and start running with. We got audio processing, so we have a harness that will read a file and allow you to write a file. We have image processing where you can read and write image files, and then we have starter in different areas. We have various examples that can start you off, and so we've got a few people that have been helping out. Sebastian, Hui, Crisilio. I'm available to help. So we're going to have essentially an hour and a half of free project time, so you can continue the problems and that we had in the earlier session, and you can also start to work on things that are kind of in your area that you're interested to see how they play out in Chisel, and we're here to help you get them off the ground. Are there any questions? So you start with your hello project and start modifying that to get it to be more in line with what you want.
I was just wondering, in some places you have object keyword, and what does it really mean?
And as contrasted to class.
Yeah.
Okay, so what it does is it introduces a namespace that we would start with that name that you give to the object. And so if it's, for example, let's see, blimp, it would be blimp dot and then the name of the internal methods. So all the methods defined in that will be in that namespace at top level. So it's like, have you used Java before? So
yeah.
There's a math class, and then there's class methods. It's like class methods at top level. So you say, and class variables that are global but within the namespace of that class. So you'd have math.py, and then you'd have these there. So they're not associated directly with instances of the class. They're things that are global but pertain to that particular potentially that class if it's companion. So there's two cases. One where you do it independent of class definition, and you just want to introduce a new namespace. And then there's the second one where you do a namespace in conjunction with defining a class. So you have class blimp and object blimp. Okay. And now you're introducing all the class methods and class variables, like the number of blimps. That's a variable that's associated with blimps. So you want to put that in the object blimp. Then there was the other one where you just do it independent of classes, and that was even filter.
Right.
You say object even filter, and you can do apply method. That means that I can then do even filter and apply that name to some arguments. So the apply method in the object definition is invoked when you use the name given in the object definition.
So, is there any example of how the objects are actually used, or what is the motivating example for the objects or something? That...
Let me go back to blimps. Okay, so you can have, corresponding to the class blimp, you can have an object blimp, and you can have the number of blimps be a variable that's associated with blimps, right? But there's not one of those per instance of blimps, but rather one for all blimps.
So it's like a static member.
Yeah, it's a
of the
static method. Yeah, that's what I meant to say. Yeah, thank you. Some other people call it class methods, but yeah, it's like static method. It's at top level. You're introducing a new namespace, right? So you can access it by blimp.numBlimps, okay? But notice here, I can just I can call an apply method without using dot, because this is what gets called when I just call it like a function. It calls the apply method. Okay?
Right. So you call it without instance name, essentially.
Yeah.
Because it's one per.
That's what. So the apply method is like a factory method for that object. It's like so. Oftentimes you can do factory methods. So if you put that like here, you put this in conjunction with a blimp class, then you can make a blimp factory like right here, right, where it will count the number of blimps every time you make a new one, which you might want to do.
So if I understand correct, that this code you're showing on this screen wouldn't work unless you previously had class blimp.
That's right, yeah. So I guess I'll just show the other use of it, which is this one here, where we had object single filter and object even filter, and only introduced this to be able to write just a single function that's called single filter. Okay, so this will be available at top level, so you can just call single filter and it will construct this particular kind of predicate filter that filters out or just keeps things that are single digit. Any other questions?
But then, I guess if you call it, it just returns the object of type of this the filter object, right? That.
Yeah.
Okay.
Yeah. But I guess what I'm not showing, just next level of complexity, is you could imagine having a bigger category and having a lot of methods at top level here, and then you have to use the dot access, and they could be not associated with the class. You just want to introduce them and package them all together,
Right,
as static methods.
So it can be just like a package.
Yeah, and then you have to say import if you want to get them without having to prefix them with the object name. Otherwise, you have to do the same thing like blimp.numBlimps. But if you say import blimp.underscore, then you get those without having to prefix them. Okay, we're going to move on to the final section. I guess before I do that, I just want to put out some of the URLs and ways to keep involved. Obviously, got the website. We've got a mailing list. Our code's open source, modified BSD license. It's available on GitHub. We are tracking feature requests and bug requests through the GitHub. And we've started a Stack Overflow, Chisel tag, and Twitter. We got a way to communicate. But if you want, you can contact me directly through my Berkeley email address. And thanks for everyone that helped out and the funders. I think right now we're interested to hear your feedback on Chisel and on the boot camp and how it went and how we could improve it and what you liked and didn't like about Chisel and the boot camp. So, who'd like to start?
I liked the fact that you included solutions for all the examples that we could go through, so this way we could do it ourselves, and then if we got stuck, just dig it up and continue to proceed and make progress with it. The biggest problem I had doing the working through the examples was due to the slowness of the EC2 instance. It was taking about 75 seconds to get through each make run cycle, and that made it somewhat slow to follow along with the examples while we were running.
Okay.
I'll just second about the EC2 slowness. I worry that I think one of the arguments that is being made with Chisel is that it's a way to quickly prototype different changes in hardware, and when it takes that long to compile a simple program, it falsely undermines that premise somewhat. I don't know if other folks were using the VirtualBox setup that's available on the Chisel website. That is much faster and just as easy to set up. So I maybe in the future do more to promote either get faster EC2 somehow or do more to promote folks installing the VirtualBox setup on their home machines before they come.
So even with VirtualBox, it wasn't really that fast on my computer, which is fairly recent. It takes about 6 seconds just to catch a syntax error. That's pretty slow, and syntax errors aren't just pop up all the time. So just getting that speeding up would be faster. Would be nice.
Okay, let me just give one way to run it that's a little faster. So you can actually stay in SBT. A lot of time is just firing up Scala. So if you just start SBT, then you can interactively fire up commands like run, and the time is less. So for example, you can just type in SBT and then hit run repeatedly until the syntax errors go away, and you amortize that startup cost. Anything else?
Hey, Jonathan, I was going to follow up on the EC2 comments. What I realized a bit after the fact was it came up in the slides later on. I could do git pull and one other magical incantation, or perhaps it was just git pull in my Mac shell, and I ran it local on this MacBook Pro. Way faster, way better than EC2, and super simple.
Okay, thanks.
What might be helpful for us to understand, since you guys have done this on 5 chips or more, what are some of your benchmark numbers in terms of the compile time or the iteration cycle? What do those look like? Are those minutes, hours, days?
Well, okay. And we got some students that have been building the chips, Chris and Ben actually. So.
Well, I'll just say on the Raven side of things, that's one of the chips that's used this. The compile time, so Chisel to Verilog compile time is small number of minutes. Going from Chisel to building a C emulator that can emulate the whole processor that includes a vector unit and all this is also on the order of minutes to compile and run a benchmark test on the processor. So it's pretty snappy. Making changes to the RTL is definitely the least time consuming thing of taping out the chip.
No, it's like 2 minutes to build the Chisel. I mean, with our processors, it's like maybe 2 minutes to go to Chisel to whatever your backend is, and then the backend compile time is maybe a few more minutes on top of that. But it's especially if you just want a C++ simulator, it's really pretty quick to start running through your tests.
All right. So this is for pretty sophisticated processor design. Yeah. Hold on.
Bottom-up view would be nice to also. There was a really great bottom-up view, and you also had a few slides where you showed how the Chisel language abstracts some of the features of and goes all the way down, and how much code you'd reduced. But it'd also be really nice if we could also get maybe Suder and go through an architecture and just kind of decompose it into its pieces and see, so it can kind of complement the bottom up with the top down. That would have been useful to me.
Okay, so one thing to look at is what Chris wrote, the Sodor processors. I think they're really well written, and they're pretty educational to see how that was. But I think I could have done more, top down on a processor or something to show how you compose all the pieces. Yeah.
Yeah, I second that. Wanted to see complex designs and really advanced things you can do.
If you want to see some advanced things to do, if you look in the Chisel source code, it's under ChiselUtil.scala. You can see some really clever Chisel code on doing something like, say, like a bit reversal. You can see like a recursive, Scala function that does that for you. So that's where I've seen some of the more cool Scala features used to create awesome Chisel code is in ChiselUtil.
Cases where you do a lot of streaming, so you have, full and ready bits, and you abstract above the sort of back pressure interface that's complex.
We do have queues in ChiselUtil.
And arbiters that propagate the ready valid signals. But maybe you were talking about something else.
Oh, yeah, that's what I meant.
Yeah, okay, yeah, I know.
Yeah, ChiselUtil is a good place to see some of the stuff that we've made public so far. Okay. Some of the cooler stuff.
Have you guys considered writing like a cookbook based on experience of writing tutorials over the processors?
I don't know if we figured stuff out yet. That's kind of the weird thing when you have a new language is what is the correct style? We still argue about how to name things and how to break apart components and what is the best. Do you have a 500-line component? Do you have a 100-line component? We still argue about this stuff.
So one of the things that we have as ongoing research is how to describe some of those ways of writing code as patterns, like done in software. So we're hoping that we can not only articulate the patterns, but actually expose them as Chisel libraries. So you could actually write a function to actually implement the pattern. So you can just start to design using patterns. So that's one of the things we're working on. So actually, we've got some of that in Chisel Util standard library. And we hope to I think that's probably our next thing that we really want to push hard is higher level, more reusable modules and patterns, and create something like a SOC toolkit that you can stitch together things really easily and apply patterns and just raise the level of design up another level.
One possibility is maybe take something like an ALU 8 bits to 64 bits and show it going from Chisel all the way to FPGA schematic sent in async layout. So you see the entire flow. That would be helpful, I think, at these kinds of boot camps. Some data points on the actual iteration cycle for those would be helpful too.
So, one of the challenges in doing a boot camp is trying to figure out how to allocate time. So what would you like to have a bigger day or replace, did you find some of the stuff not as useful? How would you think would be a better way?
So I thought the hands-on lab session at the end, that we did was good, but I would have liked to have seen a very structured thing for those of us who weren't trying to work out independent examples. So if we could get, you wouldn't have to be anything somebody would go over, but just continuing to go through, kind of a page-by-page tutorial, just working with the tools directly would be nice. And one example of something that would be fun to do would be to actually, go through, do the simulation, go a little bit further than just the verification that the Chisel program implements the thing we're trying to implement correctly, but then go through and actually try to do the simulation and get some kind of performance metric out of it. Because that's something I think a lot of people would be interested in doing, where a lot of the more fun simulation capabilities can be made very useful.
So how did people find the language itself? What was good and bad about that? Did you?
I think there was a learning curve that comes from Scala, both the power and the learning curve. So I don't know about other folks in the room, but I kept writing equals and then getting a strange type error that I had to then say, what? Oh, I had to use triple equals for value equality versus reference equality or whatever.
Yeah.
I found at times that having to do explicit type constructors from constants to uint of constant or to bool of constant or whatever was a little tiresome and noised up the code. On the other hand, at least it was explicit what I was doing there. I think if you're using this as a tool in universities in computer science and engineering departments where the students are exposed to modern programming languages, I could see that there'll be good take-up of Chisel. I'm thinking about then the broader engineering community of hardware designers that have been using Verilog and VHDL for a long time, and I think you'll find a very steep learning curve for these guys. They'll be surprised about when they use brace brackets versus round brackets versus square brackets, let alone some of the other challenges. So it feels like there's still a couple of years of maturation in the tools. A couple of places where I made a mistake, I got a blow up in the Scala in the Chisel library, and that should never happen in a library that you're hoping to get mainstream adoption. It needs to be so defensive that it says, oh, you're doing a thing here, rather than I got halfway through instantiating a thing and I'm giving you a stack trace because I had an exception or whatever. Let's see. That's it for my language comments. I don't know.
In terms of a lot of language things, I think a cheat sheet would help, because curly braces versus brackets, how do you access an array, that kind of stuff, and even just what the arguments are, because they're not always that straightforward.
If you do a cheat sheet, it would be valuable to separate the kind of, here's the cheat sheet for Scala and here's the cheat sheet for Chisel.
I wound up going back and forth and figuring out whether I wanted it to scala notation or something like Chisel.
Also, you did a
Can you get the microphone?
It's okay.
Okay.
Just a comment. I mean, I'm kind of rusty on my RTL skills as well, but it's using Verilog. It was quite clear what the logic needs to do. I think there is a steep learning curve to understand the timings and the exact, the assignment that you expect to actually happen under Chisel. Now it's good because you actually remove a lot of the overhead, so it's much easier to write it. But people who are used to expect a RAM to be read at a certain point, a register to be assigned, I need to go to the example to actually understand why my RAM isn't read at all. And the errors I got from the Chisel weren't very clear. How I need to address it. But it is a very compressed and much higher level language, so it is the direction to go. But you need to help us get there to actually use it much more efficiently.
So mine was really about, and you did some of this in that one example, but there was a lot of overloaded operators that gave it the expressiveness of Chisel and some of the benefits of the abstraction level. But it'd be nice to kind of go through in a document somewhere that said, okay, here's what this operator does, here's the code that it's essentially generating under the hood, so that way you can get an intuitive understanding bottom up what the abstraction levels are, so you know what code is being generated into Scala or not. That would be useful for me. I don't know.
Perhaps a Chisel for Verilog designers tutorial where you say, here's the idiom in Verilog for making a module, for making a register, a wire. Where did the wires go in Chisel? What about those registers that are not actually clocked, but they're assigned to in an always star block? Where did those go? And so forth, to give them kind of a Rosetta Stone about which concepts move directly and which are a bit different.
So I was confused in the beginning with terminology of Scala. For example, what is the class definition versus the object versus the instance and so on. So I think it might be useful for people in the beginning to get general terminology of Scala, because I'm assuming that most people are not familiar with it. So.
I guess that's one of the ones that I had as well, and I think I finally came to realize, and please help me say this correctly, but that colon equals thing is really just a Chisel thing and not a Scala thing, and there's like a distinction almost between you're writing Scala here. It's almost like you have inline Scala with this kind of hardware description language, and I felt that was kind of neat once I felt like I was getting more synced with it, but it wasn't. It was just there's a learning curve there. I embarrassingly also attended the previous boot camp and forgot everything, but the one thing I remembered was there was this, I felt like there was a lot of more higher level view in the previous one where you showed went deeper on those interfaces and how the interfaces could have flips and automatic wiring of interfaces, and I felt like there was more power in Chisel exposed on the previous boot camp. Maybe that's just the top-down view, some of the other comments, but in the end, I'm really excited and promising myself again for the second time to try it out more.
So if you do Verilog or Chisel for Verilog users, one of the other things that might be helpful are things like, basically in Verilog you can generate inadvertent latches. So if there are some gotchas that you've found in Chisel or that are derived through Scala, those would be also helpful. So that way we don't make the same mistakes.
I'm afraid I got an error that I didn't understand when I actually did the equivalent of that latch, where I defined a register and then didn't assign to it on any path in my code, and I had to get help. So maybe you need to somehow capture all the Chisel code that your undergrads and grad students are writing as they write it in a gotcha file of surprises, and then say, how do we modify the code that elaborates the Chisel into the hardware graph to have better error messages for those kinds of things?
So in synthesis, sometimes you need to have some pragmas or some special rules. I didn't see any in Chisel so far. That looks like a good thing. Or are they yet to come?
Do you want any people that do more synthesis than me talk about that? Do you know what he means? Pragmas? What kind of pragmas?
For instance, there might be some special rules or do not synthesize or even simple things like that.
Okay.
If you, for instance, if you import a hard block, you don't want to touch the description of that hard block. So you might have you bound that with do not synthesize for that particular block.
I think the closest example to that is how we deal with SRAMs right now, where we have a way to memory you can specify that the read ports are going to be sequential, and then you carefully construct how you address your read ports and your write ports, and you may have to have some sort of mutual exclusion there to make sure that it stays, a one read, one write or something. And then in the back end, if I'm not familiar with some of the hacking that we do with the SRAM stuff, but we, in Chisel you can write your code such that it, understands how many read ports and write ports you have, and then if you do the ASIC backend, it knows, oh hey, this is a sequential piece of memory with one read, one write port. I know what that looks like. I can generate the SRAM for it. So I think what we do is we branch Chisel and then we'll extend the backend as we need to in that particular case. But
it's basically post-processing the Verilog to add in black boxes. With the SRAMs, you generate the Verilog and you say, I'm expecting these modules to actually be SRAMs.
Right. Yeah, the SRAMs, I guess we post-process the Verilog code. Yeah. I don't think we have any examples of, say ALU functions like a carry save adder that we, because there you have maybe a very specific target that you're trying to go after, and then you'd have to kind of post-process whatever Verilog code you generated to insert that. And I don't think there's any examples of where we've done that ourselves, but that would be kind of cool if in Chisel we had a way of saying, here's how you add additional passes. Because we do that with SRAMs, but I think that's the only real example of where we've modified things specifically.
Yeah, I think despite some inroads, it remains the case that Chisel is not a synthesis language. So if you want your transistors to look a particular way, you sort of need to do that on your own afterwards right now. For better or for worse, there's I think advantages and disadvantages of it being like that.
So a couple of times today I found that Chisel doesn't let me do a thing that I do in my FPGA instantiation. So we talked about if you use the asynchronous read SRAM, the address has to be registered. Well, it doesn't have to be registered in an FPGA. You're free to compute an address in combinational logic and feed it to a LUT-RAM. And it's actually, the LUT-RAM's delay is faster than the logic that computed the address. There wasn't a way to pre-initialize block RAM, which is something you do in an FPGA flow. It's kind of pre-initialized RAM. I know there's no analog to that in an ASIC. These are just examples of things where you want Chisel to be both kind of target neutral, but you also want to allow the Chisel user to get at the power of each of the different targets and not be in a common denominator where they can't use Chisel because there's a feature that it doesn't let them express. You almost want to allow Chisel to have a superset of functionality for its various targets, and then in the target lowerer or elaborator, it says, oh, you used a feature that is not available in the ASIC flow, or you used a feature that's not available in the FPGA flow. Related to that is this discussion of post-processing the Verilog that comes out. I never want to have to parse the Verilog that comes out of this tool to do post-processing. So in the analog today of FPGA flows with Verilog, there are ways to hang attributes off of things, and these get carried through the flow to the downstream thing, as whether it's in a file or it's some labels on the things. So there's some way to get back to, there's some way to hang a label on stuff, and then in your post-process flow that's off to the side, say, oh, by the way, that stuff over there, it had a name that was deterministically called foo/bar, and it has this property. So I hope that that kind of attribute functionality somehow can find its way into the Chisel flow.
Yeah, so I think we see that as a need for many uses and sort of annotations that get propagated through. I think another extension thing we've been talking about is documenting the internal format in the form of an intermediate form that you can have multiple passes over, like LLVM. So we can actually have people supplying tools and working with the internals of Chisel more easily. So that's a different dimension of sort of extendability and dealing with different tool flows. It's easier to then do your own stuff and add in, and so more people can support more backends.
That would be very powerful and almost as important as Chisel itself, to have a really nice circuit generator intermediate language, I don't know what you want to call it, that is amenable to multiple tool passes. That would be fantastic.
There was one at Stanford called Bex a long time ago, but that became proprietary. I don't know what happened to it.
So to finish harping on FPGAs, as a guy who would love to use this for FPGAs, if you look at the FPGA tools, if you take one of your students and say, each vendor has this file of FPGA idioms where you want to get at a particular device primitive or a particular mode on that device primitive, here's the magic Verilog that you write, whether you write it in exactly this style or you write it with this attribute hanging off of the thing. For each of those, it would be nice if there was a way to write something in Chisel that would then go through the flow and make that magic thing that you could then get at you could get that device feature through the Chisel interface. I know that's asking a lot, but that's, if you have to give up touching carry chains or telling the tool that I need the output register on the block RAM, or this is a 2-write block RAM with a 16-bit width on this port and a 32-bit width on that port and 2 byte enables and a blah, 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 then you have to then leave Chisel and go and write a black box that you then wrap with Chisel, and then you lose the integration, you lose the C++ simulation ability, and so forth. It's a really hard problem capturing all of this stuff in a way that doesn't dirty up the Chisel and make it too complicated. But that's what I'm going to be missing if I tried to build things with Chisel. Thank you.
So in System Verilog, basically in modern version of Verilog, they added a lot of stuff for verification. For example, it used to be the case that you have to have like a separate language like Vera to build test bench environments and so on. And now it's all folded into Verilog. So I didn't really get a sense of whether you have something similar in Chisel to build, complicated test benches and verification models. If you look at System Verilog infrastructure, it's really now, it's huge, right? People develop things like, OVM, UVM, and some of that stuff that I don't even keep track of. And then the second thing about verification is, again, the assertions. So it used to be that people had separate languages to develop complex assertions. And now, again, it's all folded into System Verilog. And then the coverage. So the coverage was the same story. It used to be separate languages for coverage. Now it's part of System Verilog standard. And System Verilog coverage, I wouldn't say it's actually complete solution to the coverage issue, but it is certainly very useful. Again, I don't think in the tutorial like this you can cover all these topics, but maybe if you can get a sense, if you can give a sense of how those things would be handled in the language, maybe in some very basic example or something, would be interesting.
Can you give some examples of things in System Verilog for verification that